Hi, this is Owen, and this is my project 4 for week 4 over surface area integrals and flux. So looking at the overview for our composite body, it's very same thing as last week. I've got a scalar field based on temperature going up on the body, and then we're going to look at our area Jacobian calcs and normal vector calcs. So looking at the scalar field, we can see that it increases with height, lowest at the bottom, highest at the top. You can see that with the color change. And this is how I define my scalar field and how it changes for each body for the composite. Then for the square base pyramid, we can look into our area Jacobian calculations. There's one square on the bottom, four triangles on the outside. This is my body parameterization. And just looking at the square base, this one's very basic. Looking at the cross product of dx1 cross dx2. This means that x3 is constant at the bottom, and this will output to a area Jacobi of just 1 when you plug in that constant value for x3. And then for the triangular face, I looked at an example for when x1 is constant, so x1 min would be -10. And looking at that final expression, you can see that I can take out that 1 minus x3 over 10, and then the magnitude of this 1, 0, 1 vector will be square root of 2, and that is my final area Jacobian, and that would be the same for all 4 triangular faces on this body. And then looking into this normal vector, we know that this is going to end up being 1 as well for the square base, but it's important to point out this negative for the direction. We want that normal vector pointing outside of the body. And then for the triangular face, we can see that 1 over the area Jacobian will cancel out this 1 minus x3 over 10 after the cross product is complete. And for when x1 is constant here, we can see that final vector is 1, 0, 1. So x2 will be 0. And then it's important to look at when x1 max, it's going to be positive at E1, and then when it's x1 min, it will be negative at E1. And that's to ensure that those normal vectors are pointing outwards from the body. And then for when x2 is constant, you can see that this -1 plus x3 over 10 is canceling out, and you have a final normal vector of 1 over square root of 2 times 0, 1, 1. E2 will be positive when it's x2 max, and E2 will be negative when it's x2 min. And this is all seen here in how the code is run, that x1 is negative, x1 or x1 min is negative, x1 max is positive, x2 min is negative, x2 max is positive, and then this final x3 for the square base is going to be negative. Rectangular shaft, very basic. This all turns out to 1. There's not much explanation needed there. But if we look at this normal vector, it was very easy to use additional notation to call out how these vectors are going to be pointed out on this body. So when EI is positive, it's going to be either x1 max or x2 max, one of those faces. When EI is negative, that's going to be at the face of x1 min or x2 min. And then when E3 is negative, we know we're at that square base at the bottom pointing outwards from the body. Next, for the trapezoidal prism base, this is the body parameterization for that. And we know that square base is going to be 1. And then for the trapezoidal face, very similar to the triangle, I just kept x1 constant using that x1 min of -20. And then taking that expression, getting that final magnitude of the cross product, we realize that it's going to be that square root of 2 times another expression, which that expression for this shape is -x3 over 20 minus 2. And then looking at that final normal vector for the square base, we know it's still 1, going to be negative, pointing outwards from the body. And then for the trapezoidal face, looking at an x1 constant, you can do that 1 over area Jacobian times the cross product, take out this value of -x3 over 20 minus 2, get a value of 1 over square root of 2 on the outside times the vector of 1, 0, 1. And we know that E1 will be positive when it's x1 max, and E1 will be negative when it's x1 min. And then similarly for x2, the output is about the same, just different values in the vector. So 1 over square root of 2 times 0, 1, 1. And then just looking at that final output of the code that I put in MATLAB. So when x1 min, when it's x1 min, E1 is negative. When it's x1 max, E1 is 1. x2 min, E2 is negative. X2 max, E2 is positive. And then when we're at that square base, it's negative for E3. And then I'm lastly just going to run through the code real quick and then point out one thing for my flux. You can take the time. I'm going to very quickly just run through this code. You can pause and look through the code if you want. But I wanted to point out that this value right here for the total flux, we're seeing that it's 0, 0, and then a large value for x3. And this makes sense due to the symmetry of my shape and how it should cancel out in the x1 and x2 directions, then should have that x3 value with those vectors pointing outwards. That's it that I have for this presentation. I hope that you guys learned a lot. Thanks.